most fundamental level, the interaction of matter can be described by 4 different forces. These are the electromagnetic force, the weak interaction, the strong interaction, and the gravitational force. In elementary particle physics, we are dealing with 3 of them, as the gravitational force is so weak that it does not play any significant role. According to the Standard Model, each interaction is described in a mathematical consistent way by the absorption or the emission of exchange particles. Here we will focus on the strong interaction, which is mediated by exchange particles called gluons, which act among the quarks. Gluons are responsible for the structure of the nuclei, as they glue together the quarks, making up protons and neutrons, which in turn are bound together by other gluons to form the nucleus of an atom. About 99% of the mass of the atomic nuclei, which means of the atoms we are made of, comes from the energy stored in these gluons. Doing high-precision calculations to describe the strong force in the framework of the Standard Model is so hard that physicists often refer to it as the Brown mark. In order to study all fundamental forces, scientists throughout all the world realized the largest experiment ever created by mankind, the Large Hadron Collider. The LHC is like a huge bumper car attraction, where protons are accelerated up to 99.9999991% of the speed of light and smashed against each other. During collisions, a major part of this huge energy can be converted into mass, and a large number of new particles are created, such as a very massive top quark, the famous Higgs boson, or some not yet discovered particle. The investigation of the top quark is extremely interesting because it does not combine with any other quarks to form bound states through the strong force. Therefore, a top quark escapes the gluing action of a gluon and can be observed as a bare quark. There are several elementary processes that can lead to the production of a top quark, each of which has its own experimental signature. Our group aims to provide the theoretical description for collider reactions so that one can trace back what exactly happened in the hard interaction and what kind of heavy particle was produced. This information is then used to make predictions for other processes for which are unknown, to make measurements of properties of very heavy particles, or in order to search for something completely new.